Thank you very much. I am real humbled to stand here and give the 13th Ladyzhenskaya Lecture. As Laszlo just said, this year, 2022, marks the 100th birthday of Ladyzhenskaya. So it's truly a great honor for me to give this lecture in memory of her. So my special thanks go to Laszlo and the Leipzig University for giving me this opportunity. Ladyzhenskaya was one of the most influential mathematicians in her generation. The story about what she had to overcome to become a mathematician and what she had achieved in mathematics, that has inspired a lot of mathematicians, including myself. The topics I'm going to speak today are kind of closely related to some of her works in hydrodynamics, among a lot of contributions she has done in mathematics. I'm going to give you a brief review. So I'm going to speak on fluid equations, and from Leray to and many other great mathematicians. If you search the Google Doodle, it's not an advertisement. At the 97th birthday of Ladyzhenskaya, you see they put this equation. So that's what they have in that doodle. It's a general Navier-Stokes equations. So here, the rho, it's the density of the flow, and U is the velocity of the flow, and P is a scalar valued function, denotes the fluid pressure. And we have this body force, G, okay? And here the constant coefficient is it's the viscosity constant, okay? And this term denotes the derivative, the material derivative. So roughly saying, this equation, it describes the conservation of momentum in the motion of the flow. Okay. So why we give such a equation in that doodle for the 97th birthday? Because according to Professor Nina Uratova, a student of Ladyzhenskaya, she once said that the Navier-Stokes equation, the hydrodynamics, it's the favorite topic of Ladyzhenskaya. That's from Nina think she gave the first Ladyzhenskaya lecture here. Maybe. Yeah, so that said, Ladyzhenskaya had devoted a lot of her time in the study of Navier-Stokes equations, and she made fundamental contributions in the study in this area. Okay? So where it started here, the Navier-Stokes equations. And that goes back to Leray mathematical study. We talked about that. And around the time, 1930s. So here we restrict to the incompressible flow. So we have incompressible Navier-Stokes equation. So now I'm going to write it slightly differently. And u velocity so we make it simple by setting the density to be a constant. Okay? And we have the incompressible constraint, so the divergence of the u with velocity is 0. So that says the volume of the flow is preserved through the motion. Okay. That is a set of 4 equations if we are in 3D and studied on the space-time domain. Here, omega, it's the space domain, x, and time. And often we consider a R3 case or R2. So in 3D, that's more physical, but in some situations, 2D is a good approximation as well. Okay? So relevantly, we study the 2 situations. Okay, so that's a very important, or let's say, the fundamental model, mathematical model to describe the motion of a fluid. And what is the question here, right? So the question, actually, is this one. So the central question is that, the first one, the existence of, let me put it as, strong solution for all the time to the Navier-Stokes equation. Okay? And here, what do I mean by strong? So if we are given an initial state, so the velocity is given at time 0, are we able to predict the state of the motion at any future time? Okay. So in the language of mathematics, we are looking for a solution of this PDE system with the initial data. And what it means by a strong solution, basically it says that all of the derivatives up to the second degree, the Laplace, defined, and the equations are satisfied pointwise. Okay, so that sounds a very simple question. However, even up to date, we don't have a complete answer to this question. Okay, so given a initial data as smooth as you want, do we have a strong solution for all the time? So we don't know yet in the 3D situation. Okay, so I'll put it here, 3D. Okay, so then you wonder, okay, since we don't even know whether solution remains for all the time or not, then how do we understand the motion of the flow? So then there are tools developed by, let's say, Leray. We cannot talk about strong solution for all the time, but he introduced a notion of weak solutions. So there are still ways to understand the motion, but not by talking about strong solutions. So instead, talk about weak solutions. So here in particular, Leray-Hopf solution U. Okay. So it's defined in the way that this function satisfies three conditions. So the U satisfies the equation in the distributional sense, means that we take test functions, smooth test functions, and we multiply the equations by the test functions, and then you take an integration and you move all of the derivatives to the test functions. Okay, so then even the U, the derivatives are not pointwise defined. There is a way to define the solution through the integrals. Okay, so this is one. And second, U is in the functional space, L infinity in time, and L2 in space, and L2 in time, and H1 in space. So those are the Sobolev space. Okay, and the first one says that U has finite energy. Okay, and here it's the interface in L2. Further, the solution should satisfy energy inequality. So it reads as L2 norm here from some T naught to T, and the entropy so less than. Okay, so you consider this inequality. I mean, you consider the solution on a time interval. So here it's for almost every such T naught greater than 0, and any the T greater than T naught. Okay. So if a function satisfies the three conditions, it's called a Leray-Hopf solution. It's a weak solution. Okay. And Leray showed that for this notion, for this type of solutions, there is the global existence, global in time. Leray-Hopf solution to the Navier-Stokes equation with initial data with finite energy. So it's a Cauchy problem. Okay, it's an initial value problem. U0, it's in L2. Okay. This it's true in 2D and 3D, and in fact in 2D, the Leray-Hopf solution is actually regular, or let's say strong and unique. Okay, so that's what Leray proved for weak solution, or Leray-Hopf solution. And then you wonder, okay, in 2D it's nice. It's once you have an initial state, you can predict the motion of the flow in any future time and any location. Okay. But what about in 3D, right? So now I'm going to write down the second question. Again, it's for 3D Navier-Stokes equation. Okay. For both of the questions up to today, we don't have, again, complete answer. Okay. So use the other one. So I'll talk about some partial answers. Okay. Okay, so if we go back to the time of Prodi-Seren, so there's this result proved by that was the time 1959 and around this time. Okay. So what they proved was they give some conditions. So they said that a Leray-Hopf solution in the class LP, LQ space-time is unique for the PQ satisfying Q greater than 3. Okay. So later I'm going to talk about the scaling of the Navier-Stokes equation, and this space is scaling invariant under the natural scaling of Navier-Stokes equation. Okay. So for all such class, in that class, the Leray-Hopf solution is unique. Okay, and separately, Ladyzhenskaya showed it's about the same times. Okay, 1960s. So she had a lot of work, papers, and the books. She was really productive. So around those times, so she showed that a Leray-Hopf solution is unique in the Sobolev space L8 in time, L4 in space. Okay. So if you look at this relation here, you say actually if you take P equal to 8 and the Q equal to 4, that's the special case, and that's true. Okay, so Ladyzhenskaya got a special case of the protoseron condition, and further she made a comment. She said the Leray-Hopf class is too wide for uniqueness. And later I'm going to show you some results which support this comment. Okay, so further, she showed that, in fact, this condition guarantees global regularity as well. So a Leray-Hopf solution in the class LP, LQ, for PQ satisfying the same condition is actually regular. Okay, so it's not just unique, it's regular. Okay, so later this is referred as the Ladyzhenskaya protoseron regularity criteria. Okay, so that's one classical conditional result for regularity. Okay, yeah, so now I'm going to show you, in fact, that that is possibly true. I do have some space. I don't want to waste it. So I'll put another conditional result here. So when you look at this condition, the Q, it's Q equal to 3 is not included. But in fact, that's true as well. So if you include Q equal to 3, and that's proved by Gariza, Saragin, and Schwarek. But it's a much harder case, and they prove it like in 40 years after the classical Ladyzhenskaya protoserum. So they showed that a Leray-Hopf solution in the L infinity in time and L3 in space, it's regular as well. Okay. So it's a much more difficult situation for the ending point. And you know, in mathematics, the threshold in general is the most hard one. Okay. Okay. So now I'm going to show you some recent results telling us or indicating that the Leray-Hopf class is indeed too wide for uniqueness. So write down these remarkable results by Buckmaster and Vico from the time a couple years ago. Okay. And what they showed is that they construct non-unique weak solutions for 3D Navier-Stokes equation. So the weak, here, this notion, it's not a Leray-Hopf solution. It's weaker than that, okay? So energy inequality is not satisfied, and it's not in the regularity space L2H1. It's not known, okay? But nevertheless, it was kind of the first result to show non-uniqueness for for weak solutions in the 3D situation. And the method they use, it's the convex integration and techniques, okay? And that was due to the remarkable contribution of Laszlo and Camillo. So this convex integration method, it was first, it was invented by John Nash in the study of asymmetric embedding. So that's a problem in geometry. And Laszlo and Camillo, they brought this technique to the PDE areas. And since then, a lot of breakthrough results have been made in this area, okay? And including one of here, the non-uniqueness for Navier-Stokes 3D, okay? Okay, and another one by my colleague, they showed that this Ladyzhenskaya protoserum uniqueness criterion is sharp in the sense that they construct non-unique solutions for 3D Navier-Stokes equation in space close to the border or border line of the LPS. So when you look at, it's hidden. Yeah. So it's hidden here. So basically, they took the Q to be infinity and the P very close to 2. So their result, the non-uniqueness occurs in space for P less than 2, okay? So that basically says the criterion at this ending point is sharp, this side, okay, the L2 L infinity side, okay. And they use convex integration as well. Okay. And one more interesting result, and very important, by Albritton and Brew and Colombo. It was last year. Okay, they showed that so they construct non-unique Leray-Hopf solutions to the 3D forced Navier-Stokes equation. Okay, so it's very close to, let's say, a complete answer, except that the forcing it's a singular at time 0, at initial time. Okay, so the forcing it's singular at t equal to 0. Okay. Okay, and the method they use, it's different. So it's not convex integration. They use the instability result for 2D Euler by Misha-Vishk, which this was a very important work as well. Okay, and then they managed to lift this method for 2D to the 3D, and from inviscid to viscous case. Okay, okay, so yeah, so that is about 3D. And I do want to spend some time to talk about 2D, which is an easier case, but still there are interesting questions in 2D. So I mentioned a few results of Ladyzhenskaya. Okay. So earlier we said Leray already showed the 2D Navier-Stokes equation has global regular solution. That's a Cauchy problem. Okay, so it has only initial condition. So when you consider on a bounded domain with boundary conditions, Ladyzhenskaya showed that the existence of a unique global solution for 2D with suitable initial and boundary conditions. So it solves the unique, it tells you the unique solvability of a 2D Navier-Stokes on bounded domains. Okay. Another important, very important result is on the global attractor. So that was like 1970. So again, 2D Navier-Stokes. So she showed that there exists a global attractor for the 2D flow, and we denote it by A. And moreover, she was able to prove that the dimension for the global attractor is finite. So that is very important. Okay. Of the global attractor is finite. And I explain to you why it's important later. Okay. So here she developed the semi-group techniques to study the attractor and the properties of attractor. Okay. So now I want to give you a closer look at the equation, the Navier-Stokes equation, and explain to you why the 3D is much harder and what is the challenge. Okay. 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 So we'll do some heuristics. Okay. So let's look at the equation again. I'll forget about the forcing for now, okay? Or I can just put it. Forcing is given, and you can have a very nice forcing, okay? So really what happens in the equation is the balance between this quadratic nonlinear term and this good one, which is the dissipation, okay? So when you cross everything else, just keep the ut and the Laplace, you get heat equation. And you know the solutions of a heat equation behave very well. Okay. So the bad thing, or the trouble, comes from the quadratic nonlinear term. Okay. For regular enough solution, we have a formal energy law. So when you take a dot product of the equation with u and you integrate, so you get this plus the u dot gradient u and dot u. You notice that because of a divergence-free condition, and you can move the derivatives there, you see it's skew symmetric. So if you are able to do this operation, move derivatives around, it means you have regular enough functions here. Then that one goes away. And again here, the divergence-free condition gives you 0. And what's left is this energy inequality. Did I write it already, actually, earlier? So basically, yeah, so I wrote it already, but I can write it again. Okay, so that gives us the a priori estimates. The U is in the space L infinity, L2, and L2, H1. Okay, so that's a priori estimate. And another property we use a lot for Navier-Stokes equation is the scaling property. So it says that if the function u and p, this pair is a solution for the Navier-Stokes equation, and you rescale to the way for arbitrary parameter lambda, then the u lambda and the p lambda is a solution as well. Okay, and under such a scaling, there are some scaling invariant spaces, and that is sometimes called critical spaces. So I'll write it separately for 3D and 2D. For 3D, there are these critical spaces with the embedding. L3 is 1, and H half is 1, and some Besov space, actually a lot of them. And the largest one is the Besov space. Okay. I'll explain to you the Besov space quickly, just after I give you the critical space for 2D Navier-Stokes. So in 2D, we have L2 and a bunch of Besov space, 2 over p and p infinity. Okay, so first I want to mark the important ones. For instance, in 3D, this H half and this that appears in this Escareza and Saragan-Schwarz result, the regularity criterion is L3. Okay, and in 2D, this one is very important too. And now let's look. We have the a priori estimate. It's in L2. This is the case for arbitrary dimension. So then you notice that for 2D, the energy space L2 is critical, which is very good, and I'll tell you why. But in 3D, the critical space, you don't get them in the a priori estimates, right? It's H half and L3, but here we don't have it. So the 3D is referred as supercritical. So 3D is supercritical. And for 2D, it's critical. Okay. So now let me just spend maybe 2 minutes to explain what the Besov space is, and then we do need to use it later. Okay. So roughly saying that you look at your functions in the Fourier space. Okay. And there are some bump functions in the Fourier space. So here it's the frequency C in phase space. The size 2 to q here, actually 2q minus 1, 2q, q plus 1. Okay, so you have some bump function. compact supported near the frequency 2 to the q, and that we call it phi q with the Fourier transform, okay? And then you take the vector field uq as the u convolution with the phi q. So this then it's the Littlewood-Paley projection. Okay. So here and when you take the Fourier transform of uq, you notice that it's compact. It's supported near this frequency as well, to the q. Okay, so it's localized in the frequency space, and by the Littlewood-Paley theory, this decomposition in the frequency space actually very nice, because in the distributional sense, you basically have u. It's just the sum of all of the slices. Okay, the localized one. Okay, and then we can define the Besov space if the uq, say here it's a p1, the L p1 space, and in front I have lambda q to the power s, and I take the power p2 and the sum over all of the q. So if that is bounded, we say that this vector field u, it's in the Besov space of S and P1 and P2. Okay. So this index is for derivative, and this one is for the LP space here. Okay, how you take the norm, and then the last one tells you how you take the sum when you put those slices together. Okay, and later we are going to just use the one with the last index being infinity. Then you take a supermon. Okay, so S and LP. Okay, so that is for the norm here. Okay. Okay, so now I'm going to give you a bit more heuristics here. I kind of ruined this board with my eraser. Okay, so now let's look at the competition between the quadratic nonlinear term and the dissipation, okay, the good one and the bad one. We just look at the localized situations. We look at the projections at the Q's shell, and then we compare the L2 norm okay. So we want to say let the nonlinear term be dominated by the linear term. So on the left, if you use Holder, gradient gives us a lambda q. Oh, by the way, my lambda q, it's a simple, it's just the way we put it 2 to the q. Okay, so it's the frequency, and uq L infinity, uq L2, and here Laplace second order derivative gives me 2 lambda q squared, and I keep the new L2. So we want the linear term dominate. So let's ask for this, okay? And then quickly you say, okay, it goes away, and take the frequency to the left. So if this quantity is small and for a very small constant, right? So then by these heuristics, the linear term dominates. So we have the good term play the major role, okay? And then you notice that just this is the norm. This corresponds to the norm of Besov space infinity, right? That's the largest critical space and the smallest critical norm. And in this chain here, so this norm is the smallest. And if this one is dominated by a linear term, then we are in a good situation. And look, all of the other critical norms, they are bigger, right? So if this is satisfied, or let's say the other type of critical norms are small, then again, linear term dominates. So we should have regular solutions. And that's the intuition behind all of these small data well-postness result in critical space. Okay, so you can roughly see it from the heuristics here. Okay. Okay, so what else we get from this heuristic is that it's actually consistent. So these are heuristics with the turbulence theory of Kolmogorov. In particular, on the prediction on a wave number, which is called Kolmogorov's dissipation number. So this is a wave number. It says, that's from Kolmogorov's 1941 turbulence theory. It says that there is a wave number we denote it by kappa d such that the frequency or the low frequency those ones below the Kolmogorov's dissipation wave number, they are essential to describe the flow. Because above this one, it's dominated by the linear term. Okay, so only the low frequency part matters. Okay, the ones below the kappa d, and by scaling analysis, Kolmogorov gave a formula for the wave number up to a constant. Okay, it takes the form the average dissipation rate and the viscosity coefficient up to the power d plus 1. So here, what is epsilon? It's the average dissipation rate. So you take the gradient u, the entropy squared, you take the time average, okay? And the d, it's the intermittency dimension, and I'm not going to tell you the definition. So this one in 3D, it goes from 0 to 3, and refers as intermittency dimension. So it tells you how the vector field is distributed through the space domain. Okay. When d is 0, the function has a extreme intermittency. Imagine a direct delta function. Okay, so that is the situation when d is 0. So your vector field, it's very rough. It's not regular. Okay. On the other regime, it's the Kolmogorov's classical regime. You have a vector field very nice. For instance, a sine or cosine. Okay. Yeah, so that's all I tell you about the intermittency dimension here. Okay, so now when you look at the two, they basically say the same thing, right? Only the low frequency matters. But from here, okay, so the upper one, it's really just a scaling analysis, it's heuristics. And here, maybe it's more sophisticated, but it's not rigorous either. It also comes from scaling analysis, but more sophisticated. So now we cannot just rely on the two and formulate your theorem and your result, right? So actually we need to make it rigorous here. Excuse me. So now I'm going to ask one more question. Can we actually identify a mathematical analog of the Kolmogorov's dissipation number? That's a physical notion, okay? Comes from a scaling analysis. So can we actually define, like rigorously, a wave number which says the same thing up there? Okay. So this is one, and can we justify the prediction there rigorously? Right? Does it really do what it says here? Okay. And now I'm going to tell you the answers. Basically, for the two, yes. And here is how. So these two questions, we do have answers, and that's obtained through a sequence of results on Navier-Stokes equation by using the method of frequency separation. Okay, so I'm going to start with a definition of a mathematical notion of the wave number. So I use it. Okay, so I actually just use the heuristics up there. I say lambda p -1 and up L infinity less than a small constant for any p greater than q. And I take such q, the minimum of that, okay? So that's my condition for the to define this wave number. And you note that if the shell Q is above the capital Q, and then we have this quantity, right, less than a nu up to a small constant. And then by that heuristics, you know, the linear term dominates, right, above that Q. And what happens below the Q, right? So we have this result. The time a few years ago, and we showed that let's say we have a regular solution for the 3D Navier-Stokes on a time interval. The local strong solution can be obtained, okay? And let's say it's regular up to some t, but it's open. And now if we impose the condition on the low mode, so that's the vorticity, the curl of the velocity, and we restrict on the low modes. So we look at all of the q less than the capital Q. So it's the region of inertia, okay? And we take this integral in time, and we look at the limb sup in the Q. If this is a small, okay, I can use the same constant, but you can take it even smaller, say half C0, okay? So if that is the case, in fact, we can say the U is regular. Actually, you can extend it slightly for a short time, okay? So it's actually regular up to the capital T. Okay, so you can extend it slightly. Okay, and let's call this condition as C of D, and a few remarks. So earlier we have this Ladyzhenskaya Lecture criterion, and here we see that if the U satisfies the Ladyzhenskaya Lecture, the LPQ, then the U satisfies this condition here, right? So it's a weaker condition, okay, and a stronger result. That is one. And we can show that easily. That's not very difficult, although it's not intuitive, because here really things are on the low modes. Okay. And you wonder about the ending point case. So if U satisfies the Escareza, Saragan, the Schwarak, so it's the ending point, which is the hard case. Okay. Does it follow that actually U satisfies this condition as well? The answer is yes, but we didn't prove it. It was a when we had the result, we were not sure. It's proved by tau. Okay. So basically, this condition is weaker than those classical ones, and some other classical ones, for instance, the Bill-Cartan-Maeda, and all of their extensions to the Besov space side. Okay. Okay. So yeah. On the other hand, it does indicate that only the low modes matters, and we know which low modes. It's the ones below these. Okay. Okay. So this is one result, and more than that, we can actually show it's really this kappa d. It really separates the dissipation and the inertial range. Yes, and oh, we're over time. Yeah, let me 5 minutes. 10. Okay, so okay, so we actually that's again a sequence of work with my colleague Cheskidov and a student around the time. Okay, so for 3D, we can find, so there exists wave number, we call it determining wave number, such that it is a determining wave number in the sense if you have two solutions and restrict it on the low modes. Okay, it's time dependent. If that's the same on the low modes, then in the L2 energy space, asymptotically, the two are the same. So this number, it is a determining wave number, and further, the time average, it's bounded by the kappa d. Okay. So we have a determining wave number, and that has upper bound of the Kolmogorov's dissipation wave number. So that says this kappa d, it does separate the two ranges. Okay, so that is the 3D result, and then maybe 2 minutes on 2D. So we said why 2D actually it's interesting. So I'll use the same board. So the 2D Navier-Stokes equation. And again, we proved that that is a recent result. So we proved there exists a determining wave number such it is determining wave number such that we have a pointwise estimate in terms of a Krichnan's wave number, which is similar to the kappa d, but for 2D turbulence theory. Okay, and a Leray-Hopf number that is to the power d plus 4, and d is the intermittency dimension. And here I want to make two remarks. So first of all, this is a pointwise estimate. It's not in time averages. It's much stronger result compared to the 3D where we can only do an average estimate. This is pointwise, okay? And I do want to mention that, so here, when the d equal to 2, so the regime of the Krichnan's, we have the estimate of determining modes. It's so when d is 2, it's 1/3, and it's in 2D. So the modes, it's the square of wave numbers. It's g to the 2/3. That is consistent with the estimate on the dimension of the global attractor So here, remember that's from Ladyzhenskaya's work. She showed the dimension is finite, and the estimate is obtained by Konstantin and Foyash and Tamam. Okay, so we kind of showed this result from a different perspective. Okay, so yeah, the questions up here, I just add one, and then that's it. Is the 2D flow intermittent or not? Because here we got this consistency in the range of d equal to 2, means your flow is not intermittent. Okay. If d is less than 2, then we don't have this optimal estimate. So that is the question. It's controversial. So the majority of the mathematicians and the physicists, they believe a 2D flow is not intermittent, so d is 2. But there are some numerical evidence show that it's not exact 2, but less. Okay. All right, I'll stop here. Thank you very much.